Hello, my name is Mahsa and I'm very glad to present our work on time window detection for data-driven simulation, which we use process mining and system dynamic techniques together. Process mining is a set of data-driven techniques that we use on top of historical data of the processes to discover the running processes or to do conformance checking to see whether the processes are in line with the planned processes and with the recorded events in our information system. Also, there exist several enhancement techniques, including performance analysis and bottleneck analysis in process mining. But most of the process mining techniques are backward looking. While you have the data and then you take a look at the data and get the actionable insight out of the data. What is important here in our work is that we want to have the forward looking in process mining. These techniques in process mining mainly are in two directions. First are simulation models, which people mostly use the discrete event simulation in process mining. And the second direction is prediction, which mainly machine learning techniques are used, and most of the time it's at the instance level. For example, for a single customer to see what's happening for the next step in the process. We want to use system dynamic modeling technique, which is a type of simulation technique at a higher level, and it's at an aggregated level, which we use a system and model a system in different variables and the interaction of the variables inside the system. This modeling gives us the opportunity to model the system in steps of the time and update each steps of the time based on the previous step. There exist two types of diagrams in system dynamic modelings, which the first one is causal loop diagram. As you can see here, you can see the effects of variable on each other in the system. The second one is basically based on the same relationship in causal loop diagram, which this one calls stock flow diagram or SFDs, but it includes the underlying equation. For example, here we have the flows, births, and deaths, which births add to the value of population and deaths decrease from the value of the population. Our general framework starts with an event log, which, as you can see, event log, for example, this is an event log of a toy example, which we use for a call center of car company. And then you can see, for example, we have case ID for customer number 10, and the activity is next call, which is done by this resource and in these time steps. So the same case ID appears here, which shows that the next activity that has been done for this customer is processing their next car request that it has, and with the same attributes. We take these event logs, we do some pre-processing, and we create simulation model, and we do validation and simulation. And then when we talk about pre-processing, it means that we come up with the data that can be directly used in the simulation techniques, specifically system dynamic simulation techniques. As we discussed, it's based on a step of time, so we have to change the data from event log in this format to the format that can be used. You can see that we have time window of daily. It means that we look at our process per day. And in the first day, for example, we have arrival rate of 180 people. And this is the average service time that happened to be for each of these arrived cases. But important point here is that this time window highly affect the quality of our simulation model and our still log or simulation log. So it is very important to capture the data in a way that they are more stable, and the system or our process shows more stable behavior for the variable. This is the main motivation of our work. So let's see what is the role of time window in our modeling and simulation. You can see here we can extract our processes in different window of time. For example, 1 hour, 1 day, or 1 week. And someone could say that we can go with the bigger time window, so we have more stable variables and values of the system. But it's not the case. Why? Because we want to have the more detail as much as possible, but yet the more accurate. So we have to choose between these possible time windows to have the most stable behavior of the system. So that includes that we can have at the end the most accurate simulation model. The time granular Time-Granularity Detection framework that we propose, we start with event log, and we start with the logical units of time, which includes day, week, and year, and so on. And also user can define some time windows based on the background knowledge. We generate the still logs or simulation logs for each of the defined time windows, and then we use these time windows to identify and remove if there is any trend in our data. Let's say that there is most of the time in the processes, for example, in a bank customer arrival per year, there is a trend of 10% increase each year. We remove these trends from our data, and then we go for post-processing of the data, which it includes that there exists some inactivity steps in our data, which they can be intentionally inactive. Let's say, for example, in a banking example, we have weekend, which are inactive, but it's intentionally, and some of them are not supposed to be, and they're happened out of the not regulation. And then by removing this inactivity, we increase the chance of having more stable data. These prepared data are used to train a model, which we treat them as a time series data. We train a model and we forecast the values. And based on the quality of the model and the values which we calculate using the forecast error, we can decide which one of the predefined time window are the best one, and we use the data based on that time window value to simulate our processes. So let's have our example of the still log or simulation log. If we define a time series value as a sequence of real values like sigma, then if we look at our system dynamic log, we can see that each column can play a role of sigma for us. So in fact, what we have in our extracted data out of event log are still logs, and these still logs are actually a time series. We call a time series model like delta, theta, that receive a sigma as a time series value and give us the expected value or predicted value for each of them. So the difference between the expected one and the real one can tell us how good the data was. So our framework, as we mentioned in the picture and image of the framework, includes several main steps. Then the first part is to discover the behavior of the variable, which we use uh, partial autocorrelation and autocorrelation of the data for that. And then we use our proposed function to remove the inactivity using the detected behavior in the last step. And after having this data ready, we use some time series model, which can be any time series modeling, but we use ARIMA model here to train a model and discover what is the error and decide on the best time window. These are basically the base step that we took, and I explained already. So we have the patterns, which shows the process behavior. We start with detecting the trend and removing them, which exist several methods, and we use them based on the nature of the data each time. And also we detect seasonality, which tells us about the strong patterns inside our data. And after this step, we have this forecasting and training model, which tells us about the errors and the quality of the extracted time series. So for the process behavior observation, let's say we have the sigma, which includes our data, time series data from one of the columns of our still log, which let's say it's arrival rate. And if we look at the example that we have here, you can see that at step 7, which is a day 7, we have a high correlation, partial autocorrelation, which shows that there is a strong pattern each 7 days. And if we look at the other diagram, which is hourly, we can see each 24 hours, we have a strong correlation between the arrival rate of the data. This function, test time step function, will show us that which of these patterns are the strong patterns. Using these patterns and the detect inactivity function, we define that which steps are actually inactive. So sometimes in the processes, we have the process that the arrival rates, like these are the registration of our website. So the registration is running, but still people don't work at the organization. The working hours or service time are captured during the working hours. So that's why we need this function to distinguish if the actually time is inactive or no, it's not an inactive time and it's just the some of the values are below the threshold while there is no activity and the nature of the process is different. Using this function, we have all of these sigmas, which are the time series values from our ST logs, and we capture them using two thresholds. We decided if they should be removed and decided as inactive steps or not. And as a result, we have a set of data, time series data, that we can train a model based on those data. So we use ARIMA model here, but it can be any other time series model, statistical models. And these data will be used to train these model and predict. So in the diagram below, as an example, you can see that we have different step of time, and we train different models for both all steps and only active steps. So in the orange diagram, you can see that we remove all the inactive steps and then we train the model, and these are the errors. So this diagram tells us two things. First is that removing inactive and periodic inactive time step would increase the quality of the model, which the previous function helps us to do that. And the other thing is that we can distinguish which one of these time windows that we had can help us to get the best simulation model based on the level of details that we want. For the evaluation part, we have used several real event logs, such as BPI challenge event logs, which are 2012 and 2017, and also we use synthetic event log. Here we have a synthetic event log, which is for the toy example that we explained. It's a call center of a car company, car agency, and we designed this model based on the values, and then we simulate the models with two set of ST logs or simulation log out of the data, one based on the daily manner and one based on the hourly manner. And our framework, we also fit these two type of the data structured logs into our frameworks, and our frameworks propose that the daily manner shows the most stable behavior. And also we prove that by using this simulation and showing the result in both direction, and we can see that the level of the errors in daily manner are lower than hourly manner. The other evaluation step that we have performed is a feasibility test on our real event log, which is for 2012. Here you can see that there exists like a strong pattern between each 2 hours in the data. So it means that the patterns of the data, arrival rates, for example, happening each 2 hours more similar to the previous each 2 hours. And then here you can see that the train model for our active steps and inactive steps, but you can see from the 8 hours, there is no changes. Why? The process is running process. So there is no periodic inactive process. That's why that after removing periodic inactive steps, still the data looks the same. So the trained error also looks the same. So also we have this information that I explained in more details, and then you can see if we have it for the day, let's say, so you can see that the higher value we have for partial autocorrelation or also autocorrelation in 2012, we have for 7 days. And also this is the time delta and different models that we train for different time windows, and shows that which one is the best to be picked as a time window of our simulation. So this is the software, part of the software that we use and we develop for our project to design simulation model, system dynamic simulation model based on our approach. And this part, the stability test of time window, is basically what we have proposed in this paper. And then you can access this code here and download it. It's a UI based and easy to use. And we would be glad if you use this software and provide some suggestion or feedback for us. Thank you for your attention, and if you have any suggestion or any idea, that would be nice, and I really would like to hear from you back. Thank you.